Over the last 4 decades, ISRO has acquired capability in a number of critical aerospace technologies. India's space program is now poised to enter a new era of testing atmospheric re-entry technologies with the Space Capsule Recovery Experiment. PSLV C7, writing a new chapter in the history of India's space program, blasted off on January 10, 2007 from Sriharikota.
4, 3, 2, 1, 0, +1, +2.
The vehicle carried 4 satellites on board. Lapan Tubsat from Indonesia, Pehuensat-1 from Argentina, ISRO's Cartosat-2, and the most special passenger space capsule recovery experiment, the SRE-1. 56-kilogram Lapan Tubsat is a cooperative venture between Technical University of Berlin and the Indonesian space agency Lapan. It is an Earth observation satellite, a technology demonstrator in control system, and carries an experiment for message store and forward system. A 6-kilogram nanosatellite called Pehuensat-1 from Argentina is intended to gain experience in building satellites and operating them. ISRO's Cartosat-2, which weighs 680 kilograms, is 12th in the series of Indian remote sensing satellites and has 1 meter resolution. It is envisaged as an advanced remote sensing satellite carrying on board a single panchromatic camera capable of providing scene-specific spot imageries for cartographic and a host of other applications. The data from the satellite will also find applications in urban and rural infrastructure development and management. SRE-1, Space Capsule Recovery Experiment, is first of its kind in the re-entry technology for ISRO and the country. SRE-1 was placed in its sun-synchronous polar orbit by PSLV C7. A forerunner, SRE is designed with the objectives of mastering the technology of re-entry of space capsules into the Earth's atmosphere after staying in space, provide a platform for microgravity experiments in space, and gain confidence in building reusable launch vehicles. The success of SRE has set the stage for many future missions of India.
The spacecraft recovery module will provide a unique opportunity for the scientific community to experiment under the space environment, especially under the micro-G conditions. So this can be used for a variety of studies, whether it is related to material science or biological science, and that platform can be repetitively used and will be a cost-effective means of conducting such experiments. Of course, the type of inputs what we derive during the re-entry and the splashdown will provide inputs to the design of the manned capsule which we may be taking up for the future.
To make the technology of re-entry of the space capsule possible, SRE was designed, modelled, fabricated and tested accordingly at Vikram Sarabhai's Space Centre, VSSC, and ISRO Satellite Centre, ISAC, with contributions from Liquid Propulsion Systems Centre, LPSC, both at Thiruvananthapuram and Bangalore, and ISRO Inertial Systems Unit, IISU. SRE is a sphere cone flare configuration with a spherical nose of about 0.5 meters radius, base diameter of 2 meters and 1.6 meters height, comprising of an aerothermo structure, spacecraft platform, deceleration and flotation system, besides the 2 microgravity payloads. The internal structure consists of the spacecraft elements like the Mission Management Unit, MMU, Inertial Measurement Unit, IMU, telemetry and tracking systems, sensor electronics and propulsion systems. The deceleration and flotation system, meant to reduce the velocity of impact and keep the capsule adrift, consists of 3-stage parachute and a float. The external structure of the capsule is made of composite base structure with a thermal protection system made of carbon phenolic at the nose, silica tiles in the forebody, and low-density ablatives at the base of the capsule. The thermal protection system is bonded onto the base structure using high-temperature adhesive. This system is meant to protect the capsule from the severe heating of the order of 250 watts per square centimeter when it travels through the Earth's atmosphere. SRE, weighing 555 kilograms, was placed into a 635-kilometer sun-synchronous polar orbit and stayed there for 12 days.
The space capsule recovery experiment is first of its kind for ISRO, wherein we are trying to get an orbiting module back to Earth. This is part of our effort on low-cost access to space, like reusable launch vehicle, which will actually bring down the cost of having payloads on orbit.
For its first mission, the 2 microgravity payloads performed experiments in the field of material science. The first experiment was on the growth of quasi-crystal using isothermal heating furnace, and the other on biomimetic synthesis of nanocrystal through biomineralization. ISRO Telemetry Tracking and Command Network, ISTRAC, was responsible for initial and on-orbit operations of SRE. After its stipulated stay in space and performing the experiments, the capsule, along with its payloads, began its journey back to Earth. SRE was first deorbited in precisely planned maneuvers, starting with the first burn of its thrusters, which placed the capsule into 635 by 490 kilometers daily repeating elliptical orbit prior to re-entry. A number of experts from all ISRO centres converged at ISTRAC Control Centre at Bangalore to command the spacecraft and carry out all the precise operations for the successful on-orbit and re-entry phases of SRE. The re-entry of the capsule starts with a deboost operation by the firing of all thrusters and further reorientation of the capsule, moving it to the edge of the Earth's atmosphere. The deboost operation lasts for 535 seconds, thereby reducing the velocity of the capsule. With the completion of the deboost operation, the re-entry of the capsule commences. The angle of flight path of the capsule into atmosphere interface at 100 kilometers altitude has to be very precise for re-entry to happen. The presence of plasma envelope leads to a communication blackout which lasts till about 40 kilometers. Traveling at a velocity of 8 kilometers per second, the entry of the space capsule into the Earth's atmosphere generates tremendous amount of heat caused by skin friction. The temperature experienced is in the order of 2000 degrees centigrade at the nose cap and 1400 degrees centigrade on the silica tiles. During this phase, the thermal protection system of the capsule safeguards the internal structure. The heat generated during the re-entry is proportional to the initial total energy, both kinetic and potential. The thermal protection system's design is a trade-off between the allowed heating rates that the TPS materials can withstand and the total heat load on the capsule. This design works on two principles of radiative cooling and ablative cooling. The silica tiles, an excellent insulator capable of withstanding high thermal shocks, works on radiative cooling mechanism. The carbon phenolic nose cap, which sublimes under entry heat load and keeps the underlying structure within the operating limits, works on ablative cooling principle. About 5 kilometers above the sea level, the 3 parachutes in SRE open up sequentially at prescribed altitudes. The parachute system is meant to reduce the touchdown velocity approximately from 100 meters per second to 12 meters per second at the final touchdown. With touchdown, the parachute gets detached from the capsule and flies away. Subsequently, a float gets inflated that keeps SRE adrift. The SRE recovery operations from the sea are coordinated by Satish Dhawan Space Center SDSC SHAR. After 12 days staying in orbit, SRE-1 splashed down in the Bay of Bengal, about 140 kilometers east of Sriharikota coast. The probable elliptical impact zone of 30 by 5 kilometers in the Bay of Bengal was earmarked and cordoned off from the safety point of view. A UHF homing device combined with a sea marker dye emitted from the capsule, which leaves a trail in the sea, makes it easier to track and locate. Airborne telemetry, shipborne telemetry, Indian Coast Guard ship Sarang and Chetak helicopter from Sarang are stationed beyond the 50 by 15 kilometers stay-out zone. The helicopter responsible to locate SRE also conducts safety test. On confirmation, a diver enters the sea waters to attach an additional buoy to the capsule. A team of divers from the Indian Coast Guard takes over and connects the flotation toroid. Before recovery, the condition of the capsule submerged under seawater is photographed. After this, the capsule is towed to the ship and recovered. The recovered capsule, along with its payloads, is sent to ISRO centers for further analysis and study. Space Capsule Recovery Experiment is a modest beginning, which will provide a low-cost platform to conduct microgravity experiments and enable the return of specimen from space back to Earth.